Hello everyone, I'm very pleased to be here to present our work on a teleoperation framework for mobile robots based on shared control. This presentation will be divided into 4 parts: background, methodology, experiments, and conclusion. Our work mainly includes the following parts. The first is human-robot cooperative control using EMG signals. The second is to develop a teleoperation framework for the mobile robots by using a hybrid shared control. The third is to utilize a haptic device to control the mobile robot with force feedback. While how to catch the human control intention and deliver it to the mobile robot. It has been demonstrated that humans can adjust their muscle contraction to update the mechanical impedance of arm during the interaction with environment. Hence, EMG profile can be regarded as a representation to indicate the human control intention. The left shows the control architecture, which includes GUI, feedback control, position velocity control, and mobile robot interface. The mobile platform is controlled at task level with position velocity control and feedback control. The right picture shows the system communication and the mobile robot model is simultaneously raised. The haptic feedback device, touch X, is connected to the master side via Ethernet. On the master side, the human partner wears an EMG sensor and moves the haptic device to control the remote mobile robot. The distance information are captured by LiDAR and the data transferred to the master side to obtain the attractive force and repulsive force. The haptic device sends position and velocity to the remote mobile robot in the Cartesian workspace. We can calculate the velocity and rotation angle of mobile robot by the above formula. We can find that the axis of the haptic device is used to control the velocity of the mobile robot, while X and Y are used to describe the motion profile of the mobile platform. In the artificial field method, the mobile robot is regarded as an object in the force field. The repulsive force field is the force field generated by the obstacle to the mobile robot, and the attractive field is the force field by the target to the mobile robot. Therefore, the mobile robot moves along the direction of the resultant force and finally reaches the target point. In this process, the haptic device can receive a force feedback and provide a stimuli to the human operator. At the same time, the force feedback can guide the mobile robot to move away from the obstacle. Here we developed a linear function to describe the EMG-based component. The human partner wears an EMG sensor and moves the haptic device to control the mobile robot. In this scheme, the mobile robot's motion is determined by a resistant force in the force field. The resistant force contains a repulsive force and an attractive force. The repulsive force propels the platform to keep it away from the obstacle. There is a distance between the mobile platform and the obstacle in the process of the mobile platform moving to the target position. When this distance d is less than a safe distance ds, the mobile robot can generate a force feedback to force the human operator through the haptic device. Two experiments are designed to work the proposed method with different environments, one obstacle and multi-obstacle. Let's watch the video. The first experiment is one obstacle environment. We did comparison with one without EMG-based component and while the other with EMG-based component. Then we did an experiment with multi-obstacles environment. Still, we did comparison, one without EMG-based component and the other one with EMG-based component. It concludes that with the EMG-based component, it's much easier to control and manipulate the mobile robot using teleoperation. Here it shows the performance of obstacle avoidance using hybrid shared control in one obstacle environment. It can be seen that the EMG-based method can achieve a better performance of obstacle avoidance in comparison with that without EMG component, in terms of minimal safe distance, resultant force, and force feedback. In conclusion, the developed hybrid shared control approach is feasible for avoiding obstacles for the teleoperating system. Here we list all the three contributions of this paper. Thank you for your attention.